Welcome everybody. I'd like to acknowledge that we are gathered today on the traditional territory of the Gidimt'en clan of the Wet'suwet'en Nation. Gidimt'en is their wolf clan. And I'm pleased today to be hosting Celia and Lorraine, regional entomologists, regional forest entomologists for Skeena and Thompson Okanagan. And I was looking at your bio, and I think combined you have over 50 years of professional experience, which is very impressive. So we're thrilled to have you here today, and welcome.
Okay. Thanks, Dawn, and thank you to the group for inviting us and Celia for including me in this when we start out. And it's a pleasure to be in beautiful Smithers. It's cooler. So today, Celia and I have embarked on adventures with subalpine fir and western Balsam beetle. So what I'm going to do is walk through, I think, what we collectively know as scientists about Balsam beetle, what I've done for research, and what it's doing to our forests, and some other things. And just as a start, this creature and about subalpine fir, but there is, it seems every time we learn something new, there's, what about this? So there is a lot of things yet to be learned. We know a lot about its semiochemical communication. There's been very good work done, mostly out of BC, about host selection. Again, Kathy Bleicher out of BC, about how they choose weakened hosts that are slow growing. And of course, we map it every year. We know where it's occurring. We don't know as much about in-stand population dynamics, outbreak, regulation, and like everything else, it's interaction and response to this changing host stresses and climate change. So subalpine fir, as per its name, and western Balsam beetle, they're higher elevation for northern species. But we also have pine and spruce. And so this is my big hitters list. So there's other organisms and tree species that affect the north and high elevations. And we've all heard far too much about mountain pine beetle, but it's the big one, of course. But if you just eliminated, there's my pointer, eliminated mountain pine beetle from this graph, you would see that western Balsam beetle is sort of the winner in terms of hectares affected every year. But you have to take this with a grain of salt, because I'm going to take a handful of rice, throw it in the room, and where each grain lands is what Balsam beetle does in a forest environment. It's just very discrete, tiny little spots of infestation, not like spruce beetle, mountain pine beetle that just roll through stands, killing very large swaths. So it's a very different organism. And then, of course, we have the budworms, eastern spruce budworm, western spruce budworm, and two-year cycle budworm that affect these elevations. So there's a number of agents impacting these forests, but we think the most damage or concern lies with western Balsam beetle, dry season diseases. So this just shows the extent of the host, subalpine fir. And as far as we know, everywhere that we find subalpine fir, we will or could find western Balsam beetle. And I think that's shown very well in this map, that this is from the 1960s to present day where we have mapped western Balsam beetle. And it occurs, now it's just a frequency chart, it occurs in most of the England spruce subalpine fir subzones throughout the province at varying levels of intensity. And this little graph at the bottom shows again the periodicity of outbreaks. And all insects have this undulating, they move up in population, they move down, they move up. And they respond to various things, and that's why we get the cycles. And don't think that just because there's not much happening from the 70s to 2000s, that wasn't it here? No, I think it was just thematic. That's when the federal Canadian Forest Service did the mapping, and they didn't always go up all these remote farming ranges. So I think a lot of the province may not have been captured. Anyway, moving along, this is just a background. You know all of this. Everything I'm gonna say today is intuitive, you already know. I'm just gonna put brackets. Really bored. So, subalpine fir is not a huge part of our prevalent timber supply, but locally, as we found out yesterday, it's really important and becoming increasingly so. And it's important for especially hydrology, capturing snow, regulating snow melt, and First Nations, their issues and concerns, and also, I'm not going to talk about invasive species, but a huge threat right now due to invasive species. So this is just how much we actually harvest in the province in the coast, north and south. And you can see this dip in each of the graphs. And that's basically when all forest is turned away from other species and logged on because of not kind of. And then particularly in the north, again, it ramped up and subalpine fir became a focus, and it will continue to be as we go forward. So what I've been noticing, and certainly in the north, Celia and our other colleagues have been noticing, is it seems like we're seeing more and more attack by western Balsam beetle. And it's in part because of the changing, aging forests, changing climates, and just everything's being amplified, windrow. And we've also been seeing other concerning cues in these forests. This weevil, which has been around for a long time, but we've noticed it also killing trees, just like the bark beetle. Lower rates, but we don't really know because we haven't surveyed or investigated for it. And of course, Balsam Leodelgid, which Celia might talk more about. It's moving from the south a little bit north up into the central and northern part of BC, and it's an invasive and it kills trees. So this is a really important slide. I know she's a biologist. I'm going to tell you the life cycle of western Balsam bark beetle, but it's really critical. I think it's critical to this whole talk. If you forget everything else, remember this. So first of all, it's a bark beetle. Bark beetles like big trees. It selects the biggest, usually slow growing, somewhat older subalpine fir in the forest. And it attacks, and all you see, you don't see a pitch dew, but you see a pile of sawdust where they go in. The male forms this nuptial chamber, sounds dramatic, and then females come in and she makes these galleries and lays her eggs. And by the end of the summer, they've usually reached sort of third instar, at which time they overwinter. Now the female or the beetles carry a fungus, of course, like most of the other bark beetles, that help overcome the host response and help in the survival of the beetle. So they overwinter, and the next summer they develop through the pupa and new adults, and then they overwinter again and emerge. But while that's going on, the female in that second summer can start to extend these galleries. She's already, inside the tree, and lay another brood. But the thing is, before it's warm enough, because she might want to just leave that tree and fly somewhere else, or these new adults are waiting so it's warm enough to fly. The females can start doing this before ambient temperatures are warm enough to actually leave the comfort of the tree. So that's a key point I want you to keep in mind. What's she doing? So what I'm going to tell you about, hopefully we'll talk a little quicker now, is just a few of the projects I've been involved in since the late 1990s, which I'm now finally finishing up. So looking at attack dynamics right in the stand as opposed to just measuring on the landscape, you know, how many hectares are attacked. So how are they doing this? What's the spread look like? Long-term impacts, a little bit on the management side, and then back to biology, this degree day development. So this first project, it was a simple aerial survey where we counted trees, and it was done by map sheet, specific polygons, and we did a GPS track of where we flew, and we counted red being current attack grade and green, and got just a percent of basically current dead for a while, live. That was in 1996 and 97. And we flew 870 polygons, so it's a pretty substantial sample size. We got the average mortality, number of stands. That we couldn't see any red attack, which was almost 200. And some stands, very few, but some stands had no attack at all. But what's of note, by 2014, we reflew these same stands. And literally all the stands had some level of attack. And there was only 6 with no red attack. And we pretty much doubled the amount of dead within these stands. And you'll say, well, of course you would, because it's almost 20 years older. You're going to. But we already had an idea from the literature how much attack occurred in a given year, and it was well above published records that as soon. So what we saw was average, and I don't like averages because of the way it's spatially chosen post, but it was about 32%. And annual was about 0.8%, but there was a wide range there. In some stands, as we found here, up to 70% were dead and killed, presumably by dry seas. And it was a very dry cold in our region in the south, where we had the highest levels of attack and annual mortality of 1.6, which is high when you think about it. We used to get quite concerned in the days of Mount Pine Beetle when we saw attack levels like that. And again, average mortality of 30% and 0.8. So from records, older records from the 60s, 70s, 80s, this seemed to be higher than what was previously reported. And this just shows by age class. This would be the first survey and the second survey for the youngest, 100 years, to the oldest, over 250 years. So you can see that there was a lot of mortality happening. So what's going to be there in another few years? Well, I sort of have an answer to that too. So we're seeing more and more deadness in these stands. So the second study I wanted to talk about was a long-term study. Foresters love plots, so I did big plots too, and square plots, because you like square and you don't get lost. So over a period of a few years, I put in these 11, should have had 12, but 11 1-hectare plots. And how I selected where, how to put them in is, I was thinking about, okay, I want to characterize what early in the outbreak or progression of the beetle through a stand looks like, in the middle, and I want to sort of be able to describe what it looks like at the end, or late phase. So just in sort of visual assessments through flying, I selected some stands and over, you know, the range of ecosystems we have in the south, where I would establish these plots. Oh, my map disappeared. Isn't that lovely? Look at a ghost. Anyway, that's.
If you look at it this great, you can kind of see the rivers in there.
Yeah. Anyway, and that's where our subalpine fir is. Anyway, up North Thompson into the Monasteries here and down to the Spias Creek area. And spread sort of proportionally within the ecosystems that contain subalpine fir in the south. So of note too is the first 6 plots that we established, we assessed annually every year to follow the attack, the development of the insect, predators, parasites, all that great biological hoo-ha that happens in a tree. We found some pretty interesting things. And then, of course, all the plots, about every 5 years, we reassess for mortality, continuing attack, degrade of the trees, when they fell down, all the other pests, everything that was happening in the tree. All the trees were stem mount, tagged, you know, the drill, plots. You knew them by name by the end of it. That's what we're doing. Not a rest. You're on the ground now. So it was a pretty interesting study. And so those are red trees, but they look kind of non-red in the slide. So this is just the characterization of the early, mid, and late phase plots. And obviously early is new or building. And by the end of, you know, the 15 to 20 years that we studied these plots, our visual estimation was pretty good. And numerically, what it came out to be is if you still have at least 80% of your subalpine fir alive and less than 10% under attack, you're just in the early stages of Balsam beetle moving in. Like I said, it's all intuitive. We do this. Whereas if you jump to the end, a late phase plot, you don't have less than 50% live stand subalpine fir and greater than 30% killed by western Balsam beetle, often a lot higher. And the middle part, yeah, we weren't that great at characterizing, but that also interfered with what ecosystem you're in and a few other issues we had. Anyway, so also I think what's interesting, we sort of locked down what others had written about and published, but first year when they're attacking, obviously the tree's green, it flashes with beautiful bright red. The second year, and it doesn't stay that bright red for long, but the interesting thing with subalpine fir, it does hold its needles for a number of years, where usually most other tree species shed their needles pretty quickly. And what's interesting, as long as the tree has its needles still intact, so in this dull red phase, you will most likely find brood inside of the tree. And even though all published data and what I see mostly in the field, it's a 2-year cycle, because that the female can lay a second brood, you have that overlapping generation. And then you have the gradual transition to what we call sort of gray, then really ugly gray, then snags, and then they start falling down. So we have a good timeline by following all these trees and all these plots of how long it takes for this transition to occur in the stand. So some takeaways, when you mush all the plots together, we were following 8,700 trees. Then the range in plots was about 250 to 1,200 trees per plot for subalpine fir. And the age on average per plot was under 100 to almost 200. So we had a good range of ages in these stands. And of course, some takeaways, as we lost a lot of trees over that time. We went from 5,400 to 2,400 trees with an average 55% mortality. And you can see here, one of my favorite plots that I will not walk through anymore because it's horrible. They're all in the ground. 80% mortality, late phase plot. Yeah. And it wasn't an oddity. There are quite a few like that. So again, intuitively, in the early, what we initially called an early phase plot, saw the largest increase in mortality. Why? Well, of course, they had lots of hosts. And so over that time period, they were killed. And the least was the mid to late phase plots again. Trees were gone. But what was interesting, and I don't have it on that slide, but there came to this sort of step density. Once you had less than 400 stems live left, the beetle just sort of went elsewhere. So you have a lot of mortality in your stem, but the beetle activity would just settle right down. So again, what you had left live in terms of stem per hectare at the end of the day in all these plots was pretty low, like very low. You know, going from almost 900 stems per hectare to close to 400 or less. That's a huge decrease. Now, even though we saw higher than this average 42% mortality in plot, what I haven't said yet is there was always this ongoing sort of 5 to 10% mortality from other things occurring, even though Western Balsam bark beetle was the main mortality factor. So again, the high level of establishment didn't change all that much by the climate. So it doesn't seem to be that they will kill more than 55 to 60% of the trees. The additional mortality is coming from your root diseases, weevils, budworm, drought, stress, everything else. And of course, trees were growing. Once all this mortality was happening, we actually got increases in volume in some of the stands. The trees were substantially releasing again and starting to grow. Okay, I'm not going to read the words, but just look at this. This is an early stage plot, lots of live trees. Red is Balsam bark beetle killed. This black line is other, and these dotted lines are the trees that are falling down. And see how now, boom, 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 boom. By the last assessment in 2019, there was fewer live trees than those killed by Western Balsam bark beetle, and they were starting to fall down. Where an exact turn the page, this was initially a late phase plot, but it was reversed. Right at the start, there was more Balsam bark beetle killed trees than live trees. There wasn't much change over time. And you get a big decrease here simply because all the Balsam bark beetle killed trees started to fall down. But the amount of live did not change much. The amount killed by others did not change much. It was mostly the smaller diameter trees, probably suppressed, subdominant, that were killed off pretty early in the stand's life. So before it hit that 100-year mark. And then a little bit of mortality. And then these are two mid-phase plots. And you don't have as clear a trend, but they still have some dying to do. But again, you get a decrease of live trees, increase of balsam bark beetle, and then the tree stands basically start to fall apart because they're all falling down in the stem. And usually from attack to what we call a snag, like really bad checks and bark peeling off, is about that 8 to 12 years, and also then they really start falling down at a quick pace as well. And Martin Watts, he's local here. He did the volume calculations for me. And there are some plots which actually at the end of the day had more volume or very close to the same volume as when plots were established. But the majority lost substantial amounts of volume, even though the remaining trees were starting now to grow again. What was lost to mostly Balsam bark beetle was very large. And so on average, what is it, 8.4 cubic meters a year was lost. So how does this happen in the stand? I just chose one, Up Mountain, sort of this early to mid-phase plots. Initially, lots of trees, clump distribution. all grouped together. At the end of the day, they had more growing space. So, but they were still that nice distribution. I don't want to get into all the spatial analysis because you can't see it very in this slide. But it's really interesting. You create, there's little symbols here with C's, all this purple and pink and yellow are openings, and they become larger and like sinuous snake-like openings through the stems where all the trees are falling down and dying, and then you get patches. So my question, because I don't know and didn't look at it, because we're seeing mortality increase in terms of accelerating mortality, is how is this affecting that slow transition of the understory regen coming through? What's happening there? And the plots are there. People can go and figure it out. So anyway, what else is happening? The most common thing is the tops are being broken off. They're losing their heads. You know, snow on top, boom. You know, all the subalpine fir. Sometimes bugworm would run through the stand, get balsam bark weevil, secondary weevils, apinius, which is an adelgid, decays, rots, wind throw, lots of mechanical damage, but no big killer like dry CDs, so just a whole selection of other little things happening. And I've already said most of this, but the key points are all factors 0.5 to 5% annually. Like 5% annually doesn't take long to get rid of most of the standing live trees. And there was 6 times more dead than live volume by the time I last assessed it. And this 300 stems per hectare seems to be the magic number. That when things stop, until presumably you get understories growing up, or again, you reach a critical size of tree that the beetles move in once more and start killing. So this one is just quick and dirty. This is moving on to the management. We know dry CDs attacks down trees. So like spruce beetle, you could fall trees, bring the insects in, remove them for management. That's a lot of work. Most companies or people managing don't want to do it. So I tested baiting trees in a grid pattern, so it's similar to what we do with mountain pine beetle, putting down trap trees in blocks and just leaving it alone. And sort of as we expected, baiting created overflow attacks. So you have little clumps of attack around your baits. But on those baited trees, it was the same as natural attack in terms of occupancy up to 6 meters, but in a naturally attacked tree, it would go well beyond that. There wasn't as much occupancy in the trap trees, even though there wasn't much overflow. So dry CDs use as down trees, but the bottom line is they're not as good as those natural trees that they choose themselves. So again, this is a really interesting part, you know. Bottom line, I would not recommend using trees. They work, a lot of work for nothing. I would actually only in some situations recommend trying to manage the beetle. I would try to manage the ecosystem and the host and the tree and see what we want out there. And the beetle will probably move along. It was a very difficult beetle. I have a few minutes left, only just about 3 minutes. So this is the best part, because I know the rest was kind of boring. It's just numbers of trees dying, blah, blah. This is about the insect. This is fun. So we have climate change, we have warming temperatures, and what I didn't say when we were measuring or looking at trees every year for 6 years, it looked like there was always about 10% of the beetle population that was in a 1-year cycle. But there's many inherent errors in sampling out in the real world, especially sampling and measuring insects. So I went, this is the majority were in the 2-year cycle. That made sense. Okay, so what are the temperature or degree day requirements for this little beastie? So what I did is reared dry seedies in 5 temperature regimes. And some were given cold snaps either at the beginning, partway through the larva stage, just pre-emergent stage, to look at, you know, the requirements of this insect. I won't go into gory detail. So usually we cut down green trees out in the field, wax them all up to keep in the moisture, cut down. And usually it would be year 2 trees that had adults about ready to emerge. Take them to the lab so they naturally attack our fresh wolves. Or we would usually bait up trees in the field, and as soon as they were mass attacked, we'd cut them down, do the same thing, cut them into bowls, bring them back to the environment chambers and rear them through at whatever temperature regime they were allotted to. And then did a lot of picking, sampling, measuring, what have you, as real scientists. Of course. It was every 3 days, so we were always there. Lots of summer students in those years. That was fun. So over 31,000 dry seedies gave their life for this study. So we have to honor them and include the guys. So it was, again, it was a pretty robust study. Lots of insects to give us the data. And, oh God, not more grouse. But this is interesting, 18 degrees. This is early instar larva, late instar larva, and then pupa and adults. These are the ones we're interested in. They stalled. It wasn't warm enough. They needed some kind of cue. Either had to get cold and they go, then we winter, or it's warm again. So we gave them a little boost, moved it to 21, and they kind of chugged along. Whereas if we reared start to finish at 21, they made it. Early instar, late instar, some pupa, and the adults. All good. Same thing as it got warmer, just went quicker. Brilliant. So the bottom line is they do not need what we call obligatory dive loss. They do not have to at some point, you know, go into that quiescent state. So physiologically, they're able to go right through. We did not, and even what we call year 2 adults that were going to overwinter again before emerging, those that we brought into the lab were perfectly capable of laying eggs. What we didn't do is watch them and go, can you fly? Fly over to that tree over there, so maybe they're not totally. But anyway, so this is just the degree day requirements for eggs, larvae, well, generals. Go away. So the bottom line is just under 1,200 degree days are needed. Yeah, I don't care. Well, what does it mean? Kathy Bleicher down at the Canadian Forest Service and her summer student kindly ran some biosim or pulled down climate data for me to get mins, maxes, so I could develop heat zones. And there's a big range, you know, from the high elevation sites to some lower elevation sites where subalpine fir occurs. Bottom line, it's within the variance of our calculation of degree days needed. It goes up to 1150 in one of the runs. So they could switch or have a univoltine life history. There is, especially, just look at this year. I bet those females were laying eggs like crazy last month. They would have a big early warm growing season. So it was worth waiting to the end. How does this, we've got more stress, we have more weird climate, warmer climate warmth that happens at the wrong time of year. These are extremely plastic insects in that they just respond. It's like, oh, I'm gonna winter now. Oh, it's really warm, no, I'm not. So how is this going to affect the accelerating even more mortality we're gonna see. So when we decide what to do with these ecosystems, how to manage these trees or which forest we're just gonna touch you, we're gonna leave you alone. Think about what this critter is doing. And I'm gonna hand it over to Celia because I've been talking for too long. So it's a long road ahead.
So, well, Lorraine set a very, very good solid foundation to launch, where do we go from here? What are the next steps? And along with her work, and within the past, several years, almost a decade, there have been a number of publications, peer-reviewed research, looking at the long-term, using long-term data sets. And they've, at the decline in subalpine fir ecosystems, and more colloquially termed subalpine fir decline. And what they found is that it's very widespread, and of course, complex interactions, because it can't be simple. And a lot of the factors causing the decline are climate related, which is really no surprise. Drought being the major factor, but also the timing of the temperature and moisture stress that is occurring. But the commonality of all of these papers seems to be that subalpine fir is being disproportionately affected by insects and pathogens as the climate becomes warmer and drier. And that's the scientific side. This is the media side. It takes on a whole new life of its own, depending if, anywhere. But I particularly found this last one in particular entertaining, which one of the four horsemen comes holding a dead tree. But it gives a whole new life and perspective from when it hits the media. So along with all this research, we identified concerns in British Columbia. And there are a number of climate change models available, but regardless of which one you look at, they all predict that tree mortality is going to increase, and we're going to see changes and shifts to our biogeoclimatic zone distribution. This leading to ecosystem vulnerability, but it also means something for the pests and pathogens, insects and pathogens that are present in our system. They can become more aggressive, or they may not. But it's not only the insects; it's all their symbiotic microorganisms, their natural enemies. Even the pathogenicity of some of the diseases can actually increase, and also it can also help with the establishment and proliferation of invasive species. And of course, any incidence of any of these mortality factors is only going to make the situation worse. Lorraine gave a great presentation on Western Balsam bark beetle. So the only thing I'm going to point out is that bright red that she was talking about, that's what's used as a signature for our annual aerial overview surveys. So it's a little bleached out right here. That only records current year mortality, so the bright reds that can be detected. And this only goes from 2011 to 2020. And she also mentioned, you see a few scattered trees across the landscape, and it's usually recorded at trace levels. But as the years go on, we've been seeing that we're getting more detections and also at higher severities. So, and this again is short, it's only from 2010 to 2022, because that's when our current region system is in place. So I just wanted to point out the fact that some regions have higher impacts than others. It would have been better to do it by proportion, really, but I didn't have the time to do that. But anyway, it's while provincially it's declining, it's actually holding steady or increasing in some other areas in particular. The Skeena region seems to be holding it up. So, but it's not only native species we need to worry about, it's also forest invasive alien species. And again, Lorraine mentioned the Balsam delgate. It's a lethal invasive. And it has 2 to 4 generations a year, and it's parthenogenic, meaning that it's females only giving rise to more females. So it has, high potential for rapid proliferation in the stand. And as it feeds, it injects a secretion that actually causes growth abnormalities such as gouting, And it produces, I can never pronounce it right, Rotholz wood. It's the compression wood. So it actually weakens the structural integrity of the tree and also makes it susceptible to breakage. So, so it really kind of makes a mess of the tree. And what we've been finding is that with the Western Balsam bark beetle, there's really no known constraints to its distribution within its host range of subalpine fir, whereas Balsam woolly adelgid can affect all fir. And it was introduced well, it wasn't introduced, it was detected in British Columbia in the 1950s, and it's been slowly spreading north and east within the province. And but think, there's maybe some mostly natural spread, but some introduced spread. But then it was introduced ornamental subalpine fir in Alaska. So it may reach the northern subalpine fir sooner than expected. So in light of the mounting evidence of all of these accumulating stress and threats to the subalpine fir ecosystem, and really there's a striking level of mortality of subalpine fir on the landscape. The forest entomologists of British Columbia, we all assembled to kind of characterize and prioritize the concerns that we had and develop a course of action on how to address them. And so we also reached out to some people that we knew, researchers that we knew in academia and other federal scientists who had either worked on it or were interested in working within the system. And one of those colleagues actually called it the Alasio-Carver Consortium. So we informally call ourselves a consortium. And what we did is we initiated a series of projects to conduct more comprehensive studies of these ecosystems to learn more about their ecology and any targeted potential management along the way. Such as the qualitative and quantitative stand assessments that were done, in the Thompson Okanagan, identifying the ecological diversity indicators and also wildlife habitat values. But the ultimate goal is to hopefully inform targeted management and restoration strategies while simultaneously safeguarding First Nations traditional values and conservation efforts. So some of the projects that we've actually started was expanding the network of the permanent sample plots, such as using the existing model that Lorraine had established in the Thompson Okanagan. So it's a long-term study to assess the stand dynamics and cumulative mortality. And we particularly wanted to expand it in the north because, as you saw with some of the graphs, as the timber supply is becoming subalpine fir is more significant, but also we're seeing a lot more activity of the Western Balsam bark beetle in the north as well. So we also wanted to do some work with the Balsam woolly adelgid and looking at its impact, distribution, and spread. So some permanent sample plots were established in the Kootenay boundary area where it's known to occur using a different population phase, similar to what was used to establish permanent sample plots for Western Balsam bark beetle, early, mid, and late phase. But its current range has, we're not exactly sure. It hasn't been surveyed since 2019. But we have somebody who's very interested in looking at the population genetics, more term like ecogenetics, looking at the source of, are there any invasion routes? Is it all just spreading from a few just individual invasions, or are we constantly getting new invasions from other sources? And also looking at the pathway, how are they spreading and where are they spreading to? And is the whole range of fir in Canada at risk? And also looking at invasion traits, which that can help predict the virulence of its capacity to spread. The third one is looking at the thermoregulation. Lorraine has done, and others have done this work already, but we plan to fine tune it, keep working on it, and hopefully, because as you mentioned, the consequences of that compression of the life cycle has really broad implications on both the temporal and spatial scales. And that work will be incorporated into predictive models there's development and test a new model looking at the interannual variations and the climatic suitability of Western Balsam bark beetle. And also there's an existing model using forecasts to project effects of climate change and stand development of Western Balsam bark beetle susceptibility. Another one that's going to be going on in the Thompson Open Mountain is looking at how harvesting and climate change interact with Western Balsam bark beetle, because as you know, harvesting creates these unnatural openings and very abrupt edges that can augment any climate stress, on the landscape. So this is actually Lorraine's project, and she'll be looking at how this changes over time, looking at recent versus older cut blocks and stand interiors. This is looking at subalpine fir shelf life with the increasing interest in subalpine fir in the timber supply in the north. It's kind of important to know how long a tree that has been killed by Western Balsam bark beetle maintains its wood marketability. So this was done for lodgepole pine and in response to the mountain pine beetle, and it was done with hybrid spruce in response to the spruce beetle. So we're doing it in response on subalpine fir in response to the Western Balsam bark beetle, and it's looking at frequency and magnitude of pre-existing and post-attack decay, the amount of checking over time, and also changes in the wood moisture content. And we're hoping to do more research. We had a very productive meeting this morning with a number of colleagues looking at the potential for rehabilitation of impacted stands. So it's not just, we don't really want to, it's not for management of the beetle itself. It's taking a more holistic ecosystem, ecological approach, assessing multiple values, not just yield. We want to take stands, make an assessment, how can we help this stand if we can, what are we going to leave behind, how do we want this forest to look in the future. So, just take a different perspective on how to, if the harvesting is going to occur, be a little more conscientious about how it's done and the future impacts of it. And we're also interested in multi-trophic interactions, whether the insects, there's symbiotic microorganisms, they're natural enemies, and how they're all interacting with the tree. All of these factors, they're all adapting to climate change. So how are they interacting, and what does that mean for the ecosystem, the ESSF? And so a lot of these projects, we're forest entomologists, so we focus more on the entomology, but that's not the only thing. We can't think beyond, there's a whole suite of disciplines that can be incorporated and that we can relate to. But we're hoping to attract some collaborators that can help us achieve this research. And of course, there are challenges. This type of work is very time, labor, resource intensive, as much of the other research is, anything involving forestry and ecology. But to attract funding, we really want to make sure that it's an investment into the future of the BC's forests. So just a few closing thoughts, because there's the evidence is accumulating that there are accelerating impacts on these forest ecosystems they have complex cascading effects, and we will hope to identify factors that contribute to their decline and be able to intervene where possible. Sometimes we won't be able to, but if we can, maybe we can do a little bit of good. And ultimately, it's imperative that we conduct relevant research to inform responsible forest management founded on robust science. And I'm just a figurehead up here. I'm just representing the whole group of the forest entomologists in the consortium, we'll say. They're from this list of people, it's an impressive list of credentials and experience. So we have the expertise, and we're hoping to get some support and collaboration. And just look at us, we're a fun bunch to work with, right? And we have great field assistants.